Hello students, welcome back. The final topic I'd like to talk about is the symmetry issue, and this is just a special case of something we already discussed in lesson 4. In lesson 4 we went through all the essential symmetries associated to graphs of equations. When we have double variable equation in two-dimensional plane, we have curves, and then by replacing x by negative x or y by negative y or by both, we can have symmetries on y-axis or x-axis or origin. We went through all those, and also switching x and y, we went through a symmetry about the principal diagonal, those kind of things. And functions behave pretty much the same. It's just a special case of double variable equation. So we have these kind of conclusions, just an immediate consequence of what we discussed in lesson 4. So symmetry about the y-axis, substitute x by negative x and see if it remains the same. Symmetry about the x-axis is substitute y by negative y and we see if it remains the same, but this thing does not apply for graphs of functions. It applies for graphs of equations, but for functions it does not apply. Part C is important too. Symmetry about the origin, substitute x by negative x and y by negative y, both of them, and simplify. Is it still the same? Then symmetric about the origin. A and C are important, B is not. Well, in lesson 4 all three were important, but here, so basically if you have, we have only symbolic expressions, so it's really hard to see what is going on with these. Let's go through with those with the examples, actual examples. Okay, alright, these are all examples from lesson 4. We have an equation, a double variable equation, so we have a relation, not necessarily a function. Well, let's see, if you graph it, you get a circle, and it has all three symmetries. Replacing x by negative x, now let's bring this one back at least to a certain degree, and then y by negative y, and finally both of them. In any case, they're all going to be killed because negative to the second power is going to disappear anyway. So after simplification, it'll remain the same. So it has all three symmetries, and you can see this picture, symmetric in every direction. How about the next example here? We have hyperbola, and then flip with respect to y-axis, flip with respect to the x-axis. What do you have? Still the same. Look at this algebraic expression. We have only second powers. So substitute x by negative x, negative will be killed. Substitute y by negative y, negative will be killed. Both of them, again, all the negatives will be killed. In the end, we get the same thing again. So we have all three symmetries. How about the last one here? X equals x squared. Yeah, okay, let's answer the question. But before looking at the graph, so substitute x by negative x. Negative will be killed because it's second power, so we'll have to have symmetry about the y-axis. As for the symmetry about the x-axis, no, that's not going to happen because y by negative y, but here y to the first power, that's odd power, so the negative will not go away. So no symmetry there. If I substitute both of them, well, x part will be gone, but y part will stay because this is odd power, so we don't have symmetry about the origin either. Let's see. We have symmetry about the y-axis only. We have x here. Apply negative x and flip back over here. Yes, indeed, I have something here. I have y here, but flip negative y, something down here, but I don't see anything there. There's no symmetry. How about this? Before looking at the picture, can you answer that? Substitute x by negative x. No, you can't because odd power. Substitute y by negative y. Again, you can't do that because it's an odd power. Negative will not go away. Substitute both x and y by negative and negative y respectively. Then it's okay because we have a negative sign from x, another negative sign from y. they'll collide and disappear. In the end, what do you get? We have a symmetry about the origin. Well, but those are for relations. How about functions? Okay, all right. Replace x by negative x, and in the end, still the same. Yeah, we stay at y equals f of x. It falls into this category here. Replace x by negative x and remains the same. So symmetric about the y-axis. Do you have an example here? Yeah, okay, good example. Terribly complicated graph, but still you can clearly see the symmetry about the y-axis. So replace x here by negative x over there, and I have exactly the same thing here. Start from here, x, and take negative x over here. Yeah, I have something here. That kind of thing is called an even function. Now, a graph of odd function, which is symmetric about the origin, goes like this. F of negative x is negative of f of x. In that case, the graph of that function is symmetric about the origin. Can you see that? Can you see that behavior? Y equals f of x. Symmetric about the origin, so substitute x by negative x and y by negative y. So let's go ahead and do that. So I substituted y by negative y and x by negative x. In the end, am I going to get the same thing? Negative y equals to f of negative x is negative of f of x. So that's a property. That's what you're going to get. And one more step, negative will be gone. Multiply negative onto both left hand side and right hand side. That's what you get, and isn't it exactly the same as what you started off with? Yes. So it fits this description here. Substitute x by negative x and y by negative y, and still the same? Yes. So you don't have to check everything here. For functions, you don't have to substitute both of them. Just substitute x in place of negative x, negative x in place of x, and see if you get negative of whatever you started with. Here's an example. This kind of function is called an odd function. And then, as you can see, we have a symmetry about the origin. We have part of the graph here, and then change x coordinate to negative x here, and y coordinate to negative y back there. And do I have a point? Yes. Point here, all right. Substitute x by negative x, flip over. And then y by negative y, flip over. Yeah, I have something here. We have a symmetry. Symmetry about the origin. So, as for standard symmetries, these two are important. A and C. And B is important for graphs of relations, but graphs of functions, that can never happen. Not this one. And then if the first thing happens, then we call it an even function. If the second thing happens, we call it an odd function. When do we have an even function? When do we have an odd function? That's something we're going to discuss in a little bit more detail in the next lesson when we study some power functions, I think, which will be a part of section 6 in this notebook. But we don't have enough time to cover everything, so section 6 will be covered in lesson 6, and section 5 here will be covered in lesson 7 or lesson 8. All right, that concludes lesson 5, and what do you think? It was worthy of its importance. Section 2 in particular was difficult, but it is extremely, extremely important. If I single out one section as the most important for entire 13-14 STEM algebra is going to be section 2 of lesson 5 right here. And then section 3 will become pretty close to second, as a matter of fact.